8, 16. These could get small really fast. So if we fix an x, right, if we fix it to a real number, then the series may converge or diverge. We still don't know, right? We still don't know. Now, this is where things get a little weird. What if I fix x to be 0 here? What if I tell you right now x is 0? Will this converge? Yeah, because this is going to be 0, 0, 0, 0, right? And the only thing really sitting here is that, right? So that sum, infinite sum, is really just that one number, isn't it? And that would converge, right? Because it's just a number. So I've just given you an example of an x right now that I know will make it converge. Now I said plug in 2 and you said, I don't know, right? We don't know. Might work, might not. So here's where things get a little weird. If we let x be a number for which the power series converges. I just gave you an example of an x that made it converge. What was the x I gave you that made it converge? 0, okay. That may not be the only number, but if we let x be a number for which the power series converges, so imagine that there is a number we can plug in that makes it converge. Then we define f of x to be equal to the power series we have a well-defined function. I don't want us to blow our minds here. This is not supposed to be like totally crazy. But do you remember we were just talking about functions, domains, and ranges, and like what you can plug in and what you can't plug in, right? We were just looking at that. What I'm saying to you is if somebody gives you a power series, its convergence and divergence depends on a few things. It depends on what that formula is, but it also depends on the x that you plug in. If you look at the x's that you can plug in that make it converge, then we can define a function as that power series, and it's well defined, meaning it has a domain. So look at it this way. If this is our function, then you told me just a second ago if I plugged in 0, it would converge, right? If I plugged in 0 into that function, it spit out, didn't it just spit out that first guy that was sitting there, c sub 0? Wasn't that what it converged to? But there might be some other numbers that I can plug in here, and I don't know what they are. Every series is going to be different. But there might be a number in there that actually goes to a number. So there might be an x I can plug in here that would make this converge. If I plug an x in here that makes it converge, then I have an output, right? Something it converges to. I don't know what it is, though. I just know it converges to something, right? So that's the output of the series. Yay or nay? Okay? But there are also some values of x that I could plug in here that would make it diverge. And those values would stay outside of this. This is my domain. These are the things that we're allowed to plug in to get convergence. Everything outside that makes it diverge is not in the domain of the function. Does that make sense? Okay, so we have a function. It's a weird function because we can't actually tell you what comes out the other side of it. Just that something either does or doesn't, right? It either converges or doesn't. So it's a strange type of function where you can't just like throw an output out. All right, let's see. Let's do a specific example, because we'll get too detached from reality if we just keep going down this road. So let's just do an example of a specific, I'm going to give you an example of one specific power series, all right? So here's your first example. It's the power series where I'm defining C sub n to be 1. Now what was C sub n in the power series? I'm going to put it over here, the formula again. C sub n was that formula out front, right? And I said that could be a bunch of different things, right? N factorial over n squared. It could be a bunch of crazy stuff. It could have -1 to the n, alternating, anything you can think of. But I'm going to start with the most simple example where it's just constantly 1. What would that power series look like? Sum n equals 0 to infinity, 1, right? It's always 1. And then x to the n. So let's start plugging in numbers. 1, x squared, x cubed, ... forever. Yeah? Anybody recognize that? Might be a bit of a stretch to recognize this. Because my question is going to be whether or not this converges or not. Let me kind of help you. Do you all know what this series is? That's a geometric series, right? Now let's start writing out the pieces of this geometric series. If I plug in 1, then 2, what does it look like? A, AR, AR squared, AR cubed, AR to the 4th, ... right? What is this? This is a geometric series. This is a geometric series. What's A? 1. These all have a coefficient of 1, right? But you see here, R is actually x for us over here, isn't it? So if I were to ask you right now, does that converge? What would be your response to me? If the absolute value of R is less than 1. That's what you would tell me, right? So I'm asking you, does this converge? If this converges if the absolute value of x is less than 1. Excellent. Good. Do you all agree with that? That's because this just so happened to look like a geometric series. They are not going to all look like geometric series. But this first example, you can see, this we've seen before. That power series we've actually seen. Now let's get our heads around this a little bit more. What does this mean? So when I tell you that the absolute value of something is less than 1, then what I'm telling you is that if you look at a number line, you've got to be somewhere in this window right here, between -1 and 1, right? Somewhere in between here. Now you cannot be 1, right? And you cannot be -1. With me? So, in other words, and this is going to come into play here in a minute, if you're ever asked to take an absolute value inequality and get rid of the absolute value, here's how you do it. You rewrite the inequality without the absolute value, okay, just like that. And then what you do is you take the opposite of this number, which would be -1, you put it on this side, and you make it greater. So x is squeezed between 1 and -1. Understand that? Let's practice another one. Absolute value of x plus 1 less than 4. I can rewrite this as x plus 1 less than 4, but bigger than -4. And now I can subtract 1 from everything. -5 less than x less than 3. So to say that the absolute value of x plus 1 is less than 4 means that x has to be between -5 and 3 for this to be true. Now, why is this important? If we were to come in here and define this as a function of x, this is a well-defined function. This is a well-defined function. If you give me an x, please, somebody provide me an x that is smaller than, or the absolute value is less than 1. 1/2? Is that what I heard? 1/2. If I plug 1/2 in here, it's going to add up to be a number. It's actually 1 over 1 minus 1/2, because we can still use the formula a over 1 minus r. So you give me a 1/2, right? Plug 1/2 in, and it sums up, spits out a number off the other side. So you have input, output, right? It's a function. Give me another value of x between, boom, it'll come out. So basically, if we were to almost look at this like a graph, it would be like, here's 1, here's -1. I would have a picture here, wouldn't I? In between -1 and 1, I'd have a picture. Because for every value you plug in, 1/2, it's going to have an output. And any number in here is going to have an output. So you'll have a picture, won't you? So you have a restricted domain. This function only lives between -1 and 1, but it's still a function in there. Copy that? Yes? Okay. Now, unfortunately, we have to make a small tweak to our formula. Because when we first introduced power series, we do it the way I showed it to you, but we have to make a small little adaptation to it. And I'll try and explain when I put it up here why it is this way. So a general power series and we say about A is sum n equals 0 to infinity of C sub n. I will give 1,000 points to anybody who can. No, I'm kidding. I can't give you 1,000. 2,000 points. I'll give 5 points on the final exam to anyone who can tell me why you think it is that we want to make this the formula instead of the formula I showed you before. I can't give you all day, though. A general power series about A is this right here. Is that formula almost exactly the same? But why is it that I would want to do that? Well, I'll try and draw this picture again that I drew, and then I'll ask. I'll open up the... Oh, those were open. Okay. This was the example I just showed you a second ago, right? We had a domain, -1 to 1, and it was a well-defined function. So this is a huge stretch. I don't expect anyone to get this, but...
Because then you don't have to focus, like before when you did like -4 is x plus 1 and you had that in absolute value, then you can take your focus off of x and just manipulate a, and then, is that it? Is that kind of...
Maybe.
So then you can establish perimeters going off of a instead of x? Is that it? Because x is...
No. I mean, it sounds like you're kind of there.
Because if we say that, if we want to see if it converges, right? We want to say it converges if x, the absolute value of x is less than 1. So then we want to say that then the absolute value of x minus a has to be like less than a. Is that, can we, is that the way that we...
I think you're kind of on the right track, but it sounds like you're veering off somewhere else now.
I'm trying to figure out if that's the technique we're doing, because you showed us that, okay, we're now wanting to set up a domain, and then how we can manipulate numbers if x is our little guy. So by adding a,
Yeah, what does the minus a in the formula allow us to do?
Shift the domain.
Shift the domain. Shift it. Okay, so I think that's close enough to what I'm looking for. I don't know if that's what you're trying to say. But look, do you see how in the previous example, we just defined a function to be this very, very nice, what was it, 1x to the n, right? And that happened to be like a geometric series. And we said that, hey, yeah, this actually is a function that looks like this. That's great. But just like we did in algebra, when we had functions, we wanted to be able to move them around, right? We had vertical shifts of functions and horizontal shifts of functions. So if we want to look at a function in its general form, then if we add the minus a in there, it allows us to move this around. So ultimately, what these power series are going to do is I'll do it this way. Do y'all remember seeing this earlier or no? Did I show y'all this? Where I gave you a function, which is in red. Forget the vertical red line, that's a problem with the computer. But where I tried to approximate that curve. Did I show y'all this? No? It would have been a while back. Okay, let me try and illustrate what's going on here. Okay, in red, make this a little bigger. Okay, in red you see this curve, right? This right here, and it's coming down like that. That's actually this function 3 over 1 plus 5x. That is a function. Everyone agree? F of x equals that. That's a function well defined. Right now, in black, I'm graphing the constant function 3. That's it right there. I'm graphing f of x equals 3. And this black function is not a very good representation of the red function, right? They don't look anything the same. Y'all agree with that? Now, what if I graph instead 3 minus 15x? Now, is that black line a better approximation of the one we just had? Of that red one? It still sucks though, doesn't it? Okay, now I'm graphing 3 minus 15x plus 75x squared. That's a quadratic now. Is that quadratic better than the line just was? Let's keep going. This is now a 3rd degree polynomial. Just keep your eye on the black curve. 4th degree polynomial, 5th degree, 6th degree. Oh, my computer's starting to freak. Okay, I think it just crapped. Wow, I only got to the 6th degree polynomial on that. Okay, do you agree here that this black curve right here is really close to the red one now? Now, not over here, right? But right in, there it goes. Okay. Yeah. Yeah, I think I'm going to stop asking it to do work. Yeah, it's still. So this right here, 3 minus 15x plus 75x squared, all of this is decent at approximating the red curve. At least in the little window, it looked pretty good, didn't it? Now imagine, this thing is really, really having a hard time. Uh-oh. It's not meant to be. Okay, so you'll have to just trust me that looked like a polynomial, like power function, right? X to different powers. And it was starting to kind of like move onto the red one. If we went out further, it would get even better and better. And it would just lay itself exactly on top of the red one. Within a certain window, it would be perfect. I mean, I'm not talking about like an approximation. They would be exactly the same. And So what we want to be able to do is say, okay, well, it looked real good here, but over here it sucked, right? So we want to be able to just move it over and be really good in that little area. And then we can kind of move it wherever we want so that it lands on top of wherever we need it to be good. Does that make sense? So the x minus a in the formula allows us to do a shift of our domain. All right, so this is our general form. All right. Now, we have about 30 minutes. We should have enough time to do at least 2 of these. Okay, so that's our general form. I want us to notice if x equals a, we have convergence. Guaranteed. Because what if I replace x with a? You get 0, and we're adding up a bunch of zeros, so that's going to converge, right? Okay, so we have convergence if x is a. So we're guaranteed, if someone gives us a power series, we're guaranteed that it has at least one number that you can plug in and get an output. At least one. It might be the only one, but you're guaranteed at least one. All right? So now I'm going to give you your first example of a general power series that's not a special case. Here it is. Sum n equals 0 to infinity of n factorial times x to the n. The question is, for what values of x, for what values of x does this converge? In other words, if we were to define this as a function, right? If I were to say, hey everyone, this is f of x, this question is also asking you to find the domain of f, right? So this question of what values of x make it converge is equivalent to saying if that's a function of x, what's its domain? All right, so how are we going to figure out whether or not that converges? Well, this isn't like the last problem where this was 1, right? And it was like just, 1 plus x squared, and it was real nice and geometric. So if we don't have a nice formula that we recognize, then we go to the big daddy. We go to the ratio test. The ratio test will tell us whether or not something converges or diverges, right? This whole thing in here is a sub n. The whole thing is a sub n. So let's set up the ratio test. Limit n goes to infinity, absolute value, and we want that, we want to replace everything with n plus 1 first, and then divide that by just that, right? So won't it look like this? I'll go a little slower here. Okay, so I didn't do any simplification. I just went right into it, n plus 1 in, and then just n, and that's it, right? Now, take this limit, n goes to infinity. Let's clean it up. N plus 1 times n factorial, x to the n times x, over n factorial x to the n. Dead, 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 dead. And you get limit n goes to infinity of n plus 1 times x, right? What is that limit? If n goes to infinity, where's this headed? To infinity, right? What do we need for this to converge? The ratio test, in order to give us convergence, we need this to be what? Absolute value of that to be less than 1. But we have a problem because this thing is blowing up, isn't it? It's becoming infinite. Now, x here is different, though. X is this new thing in here that is not controlled by this limit, right? So the question is, for what values of x can I plug in here and get a nice output out? So imagine we come in here and we fix x right now. If I fix x to be a number, and then this blows up, then this should blow up, shouldn't it? Like, give me a number, like 10 times infinity, still infinity, right? So give me a really small number, like 0.000000. Really, really small, but then times infinity. It's going to still blow up, right? Understand? If we fix an x, fix it, there's no way to stop this from blowing up unless x is what? 0. There's only one place that's going to stop this from blowing up, right? And that's if x was 0. But we kind of knew that to start the problem. Remember, we said that if you have a power series, if you can make this thing in here 0, then you're going to converge. Well, that would be 0 if I let x be 0, right? So we already knew at x being 0, this thing was going to converge. The question was there anywhere else? And it turns out that it doesn't look like it, right? The only way we're going to get this inequality to be true is if x is 0. Understand? So this becomes infinite. I'm going to put underneath here, this is going to become, if x is not 0, then we get infinity, which is not less than 1, right? This becomes infinite. If x isn't 0, then this right here becomes infinite, which is not less than 1, so we're going to get divergence. So if you want to look at this function right here, this right here, if we call this a function, then this function, if you graph it, if this is x, it only exists at one point. You can plug in 0, and that's the only thing you can ever plug into it.
If x is 0, wouldn't that be an indeterminate form that could be infinity times 0?
Oh, I'm so glad you said that. So the question is, if we have x is 0, then wouldn't this be infinity times 0? And then isn't that an indeterminate form? Excellent question. It is not an indeterminate form, but why? No?
Because if you take the limit, x is a number.
Okay, so let me show you with an example over here. If I say what's the limit as n goes to infinity of 1 over n times e to the n. All right? When I take this limit, where's this going? This is headed towards 0, right? Is it ever 0, though? It's never 0. But it's headed towards 0 times, now where is that headed? E to the huge number becomes huge. This is headed towards infinity. Is it ever going to get to infinity? No, infinity is an idea, right? So this is headed to infinity. We're saying this number is getting huge, right? Times a number that is getting small, right? Compare that to this. What are we saying here? A number is getting huge times 0. Exactly 0. Not headed to 0, exactly 0. Great question. I had a student a few years ago called me up. They were like an engineer. They were like in their junior or senior level classes of engineering somewhere. They called me up there. I just have a bone to pick with you. He's like, I remember you telling me that like in 1 to the infinity was an indeterminate form and blah, blah, blah. And basically it was the same exact question you have. He had a problem where it was something like, x minus 2 to the n, and n was going to infinity. I don't remember the exact problem. But basically, he was plugging in x equals 3, and he was getting like 3 minus 2 is 1 to the infinity, and he was like indeterminate and all this. There's a big difference here. If x is 3, then this is 1. 1 to any power is 1. But something headed towards 1 raised to something headed towards infinity is something completely different. You understand the difference? So, excellent question. It gets overlooked sometimes. It's in the limit. I think, Sophia, that's what you were saying. It's This is not headed towards 0, this is 0. So it's in the limit if it's headed to 0 versus in the limit headed to infinity, then it's indeterminate. All right. So, end of the day, this power series only converges when x is 0. Otherwise, it diverges. So if you give me any number other than 0, this thing's going to blow up and become infinite. Okay? All right, let's look at a different power series. This will be our last one of the day. And we'll spend more time on power series next class. Sum n equals 1 to infinity, 0 to infinity, sorry. Let's go with 4x minus 3 to the nth power over n. Okay, you ready? Let's do it. Ratio test. Same question. For what values of x does this converge or diverge? Remember, there is guaranteed, with all power series, it is guaranteed that it will converge at least one number. In this case, what would be the number that it would converge at? If x was what? 3/4. Right? If I plug 3/4 in here, I get 0 up there, right? So this does look like, I hope you see that this is 1 over n 4x minus 3 to the n. Do y'all kind of see that? Now, does that look like a power series? Like c sub n x minus a to the n? A little bit, right? How about this? Okay, you're going to have to tell me what I did there. I pulled a 4 out of this. You see this right here? I pulled a 4 out. When I pull a 4 out, I have to do a 3/4. But then that would have been to the n. So this would have been 4 times x minus 3/4. But all of that to the nth power. So I do the n power on each of those, and I get this. Now, that right there is my c sub n. And this right here is my x minus a to the n. That's my power. This is just, I'm just showing you this, okay? I kind of got away from the ratio test, but I just want you to see that we do have a power series here. Now, I'm going to do n plus 1 into that first. And then over that thing, but I'm going to flip it over. So I plugged in n plus 1, and then I was supposed to divide it by this, but then I flipped it. Did I change to plus there? Why did I do that? Am I moving too quick, or is that all right? No. Wrong one. Wrong one. This one was to the n, right? Here, I'll do that. There. Do you all have questions on what I've done here or no? What is left? 4x minus 3 is there in parentheses, and then also n over n plus 1. And we're supposed to be taking a limit of this. So watch how I do this. I'm going to split this up into two pieces. N over n plus 1 times 4x minus 3, absolute value. Yes? Now, in order for this to converge, what do we need this to do? We need this to be what? Less than 1, right? Well, take your limit. Take your limit now. What happens on this limit? If n goes to infinity, n has nothing to do with this, does it? N has to do with this. And what is the limit of that as n goes to infinity? Infinity over infinity, so maybe a L'Hopital? We get 1, right? So in the limit, that piece right there goes to 1. which means that we are left with the absolute value of 4x minus 3 is less than 1. That's what we need to, in order for this to converge. In order for that to converge, we need this ratio test to be less than 1. When we run the ratio test and we run the limit, we get just this, right? Because that's headed towards 1. So that just needs to, the absolute value of that needs to be less than 1. Now, let's do what we did a second ago. And let's take a look at, that's the same as 4x minus 3 less than 1, but then on the other side, what? Greater than negative 1, right? Like that. So I'm going from this step to that step. Now let's add 3 to everything. So I added 3 to every single piece. And finally, let's divide by 4. There we go. This series will converge so long as I'm in here, as long as the x I pick is in there. Is that all right with you? We're not done. We have one more thing to do. What if, does it make sense to ask myself what would happen if this was equal to 1 and equal here? So what if x was equal to 1? Come back over here. What would happen if x was equal to 1 here? What would we get? We would get that this is headed to 1, right? And we would get that this is equal to 1. Which means that this would not be less than 1, right? It would be actually 1. And what happens when we run a ratio test and get 1? The test fails, right? So if I plug in 1 here, my ratio test spits out 1. If I plug in 1/2, my ratio test is going to spit out 1, which means I don't know what happens at 1 and 1/2 right now. The ratio test isn't good enough to let me know what happens at the endpoints. So I actually, does that make sense or no? So I actually have to go check now what happens at each endpoint. All right? So the ratio test so far has told me that if you look at a number line, here's 1/2, here's 1, I know that everything in between is valid. I could plug it in there and I would get convergence. I would get an answer. But I don't know about the endpoints, if I'm allowed to plug those in or not. So I'm going to check it. Let x be 1. And where am I going to plug that in? Checking this right endpoint right now. Where am I going to plug that x in? Drum roll. To where? The original series, way up at the top. Way up at the top, right here. Plug 1 in for x. What would happen if x was 1? Sum n equals 0 to infinity. Oh, crap. You know what? Don't worry about it. This needed to be 1 because we would have had division by 0. Change it to 1. It doesn't change any of my other work. Okay? That all right? Okay. Okay, replace it. What do we get if we plug 1 in for x right here? What do we get here? 4 minus 3, which is exactly 1, right? Exactly 1 raised to any power is still 1. So we get 1 over n. Harmonic. That's a harmonic series. This diverges. Which means that we do not want to include 1 as part of our answer. Right? Now what do we need to check? 1/2. Let x be 1/2. If we let x be 1/2, this sum becomes, okay, what's half of 4? 2. 2 take away 3. Negative 1, we can't get rid of that. Negative 1 to the n over n, right? Alternating harmonic, which converges because we did an alternating series test on this already. So this converges, doesn't it? And that means we can include 1/2. Which means that the answer to this question is basically that x needs to be an element of the interval 1/2 with a bracket, 1 with a parenthesis. That's the ultimate answer that we want for the problem like this. Because you're asked in the beginning, for what values of x does this function converge, or does this series converge or diverge? Any x value out of this interval. So in this one problem, I have to do a ratio test, a couple of a limit, right? And then at the end, I get an interval, and I have to check the endpoints. And when I do the endpoints, I'm going to get a series that could look anything like what we saw in 8.2, 8.3, or 8.4. And you might have to run a test on this. So do you see how one problem alone here has a lot going on? Okay? So we will do more of this when we come back. But you can do all your homework for 8.4 now. All right? Boy, that really... Yes, ma'am. Oh, let me turn off. I'm still recording. Let me turn this off.